In this video, I'll discuss symmetry elements and symmetry operations. First of all, let us consider these three objects. Can you identify them? This is picture of a tree. This is a kite. And this is a model for water molecule. Now look at this picture. This part of the tree is clearly different from this part. Similarly, the top and bottom are different. So this tree has no symmetry at all, but it has its own identity. We can identify this picture as representing a tree. Similarly, this is a kite. If you imagine a vertical plane placed on the central line of the kite, and imagine that the plane is a mirror, then this part is similar to this part. This part behaves like the mirror image of this part, and this one behaves as a mirror image of this part. So this object, the kite, has a plane of symmetry. Similarly, here also you can use a vertical plane to cut this object into two equal halves. One half will be a mirror image of the other half, when that plane, vertical means perpendicular to the plane of the paper for the time being. That plane cuts this object into two equal halves such that one half is a mirror image of the other half. So this object also has a plane of symmetry. It also has an axis of symmetry. For example, if you imagine a line like this, and if you rotate the molecule, then this hydrogen atom will go to this place and this one will go to this place. The resulting arrangement of the atoms cannot be distinguished from its original arrangement. Therefore, this axis is an axis of symmetry. I will now elaborate on these ideas in a bit more detail. Let us first consider the simplest molecule, water. For our convenience, we will label these atoms as 1, 2, 3. And imagine an axis like this. If you rotate the molecule about this axis through an angle of 180, what will happen? This atom will go to this place and this atom will go to this place. The configuration, that is arrangement of atoms, will be like this. Atom labeled 1 will come here, atom 3 will come here, and 2 will remain in its own place. But something more happens. When this is turned, the molecule is turned about this axis, the front surface goes to the back surface and the back surface comes to the front, as if some inversion has taken place. To keep track of this event, we use a bar notation here. One bar means that the atom has been shifted and the associated orbitals or vectors have been inverted by that rotation. Similarly, 3 is also inverted. The oxygen atom is also inverted along with its p lobes, etc. It is inverted by that rotation. So this is also 2 bar. Now if you call this configuration 2 and this one is 1, then 1 and 2 are equivalent, because if you ignore these labels, then this arrangement of atoms and this arrangement of atoms cannot be distinguished. Only with the aid of these labels we can distinguish them. Otherwise they are the same. This is why the configurations 1 and 2 are called equivalent. Now, but they are not necessarily the same. They are equivalent but not the same. Now carry out a further rotation through 180 about the same axis. The axis is here. Carry out a further rotation of 180. What will happen? This atom will go to this place and this one will go to this place. So the arrangement of atoms will be like this. 3 will go to this place and the bar will not be needed now because a further inversion occurs. This 1 bar becomes 1 here and 2 bar becomes 2. Note that this is the same as this one. If you call it 3, then 1 and 3 are not only equivalent, they are the same. They are the same. Let us now consider ammonia molecule. It is pyramidal in shape. Imagine an axis like this. It is like an umbrella. You may imagine that this is the handle of the umbrella and these are sticks on the surface of the umbrella. You can rotate this object about this axis. For simplicity, we draw a figure like this. We take only the base atoms, that is hydrogen atoms. We call it 1, 2, 3. 1, 2, 3. These are the positions of hydrogen atoms. And nitrogen atom is somewhere here, above the plane of the triangle and on a vertical line. Now, if you rotate this, the axis is like this, and you can rotate this through an angle of how much? This angle is 120. So you can rotate this through an angle of 120 about this axis. What will happen? One will come, if you carry out a rotation anti-clockwise, then one will come here. You will get a similar triangle. One will come here, 2 will go to this place and 3 will come here. But no inversion occurs. A rotation in this manner will not invert the lobes or vectors associated with the atoms. So no bar rotation is needed. You can rotate through a further angle of 120 about the same axis. What will happen? You will get a new arrangement, new configuration. 2 will come to this place, 3 will come to this place and 1 here. This is also not the same as this one. Now carry out a further rotation through an angle of 120 about the same axis. What will happen? 1 will go to this place, 2 will come to this place and 3 will come to this place. The resulting configuration will be this one, the original one. So 120 rotations 3 times will produce the original configuration. This axis is called a threefold rotation axis. It is denoted by C3. This number 3 comes from this fact. 360 degree divided by 120 degree is equal to 3. We can carry out 3 rotations to complete the cycle. So this is a threefold rotation axis of symmetry, and this one is a twofold rotation axis. This will be denoted by C2. A twofold rotation axis, this 2 comes from 360 divided by 180. Next, let us consider reflection. What is n-fold rotation? A Cn axis, an n-fold axis of rotation means that a rotation about this axis through an angle of 2 pi by n, where n is an integer, will produce equivalent or identical configuration. A Cn axis is a line through the object such that a rotation of the object through an angle of 2 pi by n about that axis will produce an equivalent configuration or an identical configuration. Now let us consider reflection. Reflection, consider the same molecule, water, 1, 2, 3. You can imagine a plane of symmetry like this, cutting the object into two equal halves. A reflection plane is denoted by sigma, plane of symmetry, and the operation will be denoted by a reflection operator, sigma operator. What will happen if you carry out this reflection? 1 will come to this place and 3 will come to this place. Oxygen will remain in its own position. 3. This becomes 3. This becomes 1. 2 remains in its own position, and no bar notation is needed. Bar notation is needed because reflection on this plane will not cause any inversion of associated vectors. If you carry out a further reflection on the same plane, what will happen? You will get the original configuration. 1 will come to this place and 2 will come to this place. This is 3, this is 3, and this is 2. This is 3 and this is 2. Now, this is the same as this one. Therefore, we can write that sigma operation carried out twice will produce an identical configuration. This operation, that is doing nothing, just identifying and doing nothing, is this configuration. So this operation will be denoted by E operation. E comes from the German word Einheit, means do nothing. Similarly, you can imagine another plane like this. A plane on the plane of the paper, cutting the object into two equal halves. This atom will be halved. One half is on the upper surface, the other half is on the lower part. Similarly, each atom is cut into two pieces, and if you carry out a reflection on this plane, if I call it sigma primed, then what will happen? The atoms will remain in their own position, but the atomic orbital lobes or vectors associated with the atoms will be inverted by a reflection on this plane. So 1 will become 1 bar, 2 becomes 2 bar, here is 3. 3 becomes 3 bar and 2 becomes 2 bar. If you carry out a further rotation, a further reflection on the same plane, you get the same configuration back. Sigma primed again. So sigma primed square carried out 2 times on the same plane will produce identical configuration. So we have got 3 symmetry elements so far. What are they? I am writing here the elements, symmetry elements and symmetry associated symmetry operations. The first symmetry element is identity of the object. You have to identify first, then you can carry out other operations. So identity is the first symmetry element and corresponding operation is do nothing. Identify it and then leave it undisturbed. This is do nothing operation. It is denoted by E cap, E hat. This is needed just as 0 is needed in the number system for addition and subtraction. 1 is needed in the number system for multiplication. Similarly, E is needed for developing the symmetry operations in mathematical forms. To develop the algebra of symmetry operators, we need this identity operator. Next comes rotation operator, Cn. Cn axis. The element is a Cn axis, that is an n-fold axis of symmetry, and the corresponding operation is Cn. If you carry out such operation about the same axis r times, that will be denoted by Cnr. This means that Cn operation has been carried out r times, where r is an integer. This r is either less than or equal to n, because Cn will produce identity. Cn carried out n times will produce the original configuration. This is E. And then we have the plane of symmetry sigma. The plane is denoted by sigma, and the corresponding operation, reflection operation, is denoted by sigma with a hat. I intentionally use the hat notation for the operators. In textbooks, this notation is not used. Both identity element and both symmetry element and symmetry operator are denoted by the same symbol, but that may sometimes lead to confusion. That is why I am using a distinction here. I am distinctive mark here, notation here. Symmetry elements will be written without hat, and symmetry operations will be written with a hat. There are two other symmetry operations, improper rotation, Sn, improper rotation axis, Sn operation, and inversion I. Inversion operation is denoted like this. To discuss these two, we need to examine commutability of rotation operation and Cn operation. This is needed first. If you have an object, you may carry out a Cn operation and then a reflection operation, see the result, and do the same in the reverse order and see the result. If these two may be the same or may not be the same, under what condition these two will be the same is a very basic subject, and on that we will determine whether these operations can be carried out or not. This will be discussed in a next video. Thank you for watching.